Hello everyone. In this time we are going to see how to use the capture function of the CCP module in the PIC18F45K50 microcontroller. CCP stands for Capture, Compare and PWM. The capture capability is used to track time events. We are going to take advantage of the CCP module to get events by detecting the rising edge of a pulse, its falling edge, every fourth rising edge, every 16th rising edge. We have two CCP modules in our microcontroller. For this example, we are going to use the CCP2 module. Suppose that we want to know the frequency of certain digital waveform. The first thing that we must know is the period. In order to know the period, we must track the difference between two rising edges. The CCP module makes use of either timer 1 or timer 3 to track time events. The selected timer will be running all the time. So, we must instruct the CCP module to detect a rising edge. When the CCP module detects an event, a flag is activated. This flag is going to serve as the signal to record the occurrence of time of the rising edge. This flag is going to serve as a signal to record the occurrence time of the rising edge. Timer 1 and timer 3 can be used as 8-bit timers or 16-bit timers. Since we don't know the frequency of the waveform, and it could be a very long one, we are going to program the timer using 16 bits. When the flag is activated, that is to say for our case CCP2 interrupt flag, automatically the contents of registers timer 1L and timer 1H are copied to CCP2R2H and CCP2R2L registers respectively. We don't have to do this manually, but in order to know the difference in time of the two rising edges, we must save the time of arrival of the first rising edge in an auxiliary pair of registers. We are going to save the time in reg 0L and reg 0H. When the next rising edge arrives, the flag is activated again. The timer's registers values are copied again to CCP-R2H and CCP-R2L registers, and we are going to save this time to reg 1L and reg 1H respectively. When we have these four values, we are going to subtract reg 1L minus reg 0L and reg 1H minus reg 0L. The difference is going to tell us the period of the pulse. We are ready to program the algorithm in MPLAB in order to simulate what we were reviewing in the past section. The first thing that I'm going to do here is to include the proper registers and libraries for our microcontroller. Then I'm going to reserve some memory space for our registers. I don't know if you guys remember the names, but this one I'm going to reserve 00H now locations from 00 through 5 hexadecimal. Okay, now our main program. Go to start. And the first thing that I'm going to do is to clear the analog functions of the port C. Then I'm going to declare my pin RC1 as an input pin. You guys need to go to the datasheet in order to know what is the pin that is tied to the CCP module. In this case, CCP2 module is tied to RC1 pin. At this point, it is necessary to review several of the registers that we are going to be using in order to know how they are organized. The first one that we are going to see is T1 control, timer 1 control. And as we can see in the upper 2 bits, the timer 1 clock source is going to be our oscillation frequency over 4. That is to say the time, the machine cycle. Next, the prescaler, we're not going to use any prescaler. Our secondary oscillator is going to be disabled, and I mean there is no point in synchronizing our timer number 1 to an external input. We decide to program it as a 16-bit timer, and in this time we are going to have our timer off. So in timer 1 control we are going to store number 02 hexadecimal. Now let's review the CCP2 control. As we can see, bits number 7 and 6 are in use. Then bits number 5 and 4 are devoted to PWM duty cycle. We're not using them. And the lower nibble is the one that holds the configuration to capture or compare, as we decide. In this case, as we are going to be capturing a time event, we decide to capture every rising edge of this event. So I'm going to put 0101 in those bits. In CCP timers, we are going to store B8 hexadecimal. Okay, so I'm going to program now my T1 control register. Now my CCP2 control. And finally, my CCP timers register. Now, maybe it is convenient to get a track of the CCP pin by means of an interrupt. So at this point, maybe it is convenient to program an interrupt, a low priority interrupt. Then I'm going to enable it. Just to be safe, now it's going to be disabled. My timer is going to start running right now. And I'm going to clear all my registers I want this to be trapped here. Now I'm going to program my interrupt service routine. I'm going to put it in, let's say, origin 0 to 100 hexadecimal. And the first thing that I'm going to be doing is to clear my flag. And then I'm going to move from my CCP R2L register to my rec0L, and then from CCPR H to rec0 high. This is going to be the registration for the first rising edge. Okay, I've just saved the time of arrival of the first rising edge, but I need something to know if this is the first rising edge or the second. So I'm going to be using a flag. I'm going to check if this flag is active or not. The 0 bit of regx is going to be my flag, and if the regx 0 bit is active, then I'm going to branch to second. But if this is the first time and I've already moved the contents of CCPR2 register into rec0, then I want to activate this flag. Up to this point, if this is the first, then I'm going to wait for the second. I'm going to branch to leave. If this is the second rising edge, I'm going to move my CCPR2, but now into rec1 registers. Another thing that I have to do at this point is to get the difference in time of that couple of registers. So I'm going to move the contents of my rec0L into the working register, and I'm going to subtract this value from register 1L, leaving the contents in this same register. Now I'm going to move it to the final register, that is going to be register 1L into rest L. And need to do this once again, but now for register 1, and instead of make just the subtraction, I need to take care of the borrow bit. So register 1H, I leave it in there, register 1 into res high, and I need to be prepared for the next catching of the rising edge, so I'm going to clear my auxiliary flag, and I jump out from the interrupt service routine, and if you remember, I need to put here a tag that is going to be called leave. Another here, interrupt CCP2 interrupt service routine. I almost forget that I need to program my interrupt vector located in 18 hexadecimal. I need to check if my flag is active, and that's it. This is ready. Let's compile this to see what happened. And oops, yes, obviously I forget my register that is going to be serving as an auxiliary flag. So this is 06, and another one. Do not forget to do this always, guys. We're ready to go. Okay, let's simulate this. I have programmed a series of stimulus here. The first stimulus is going to be in time 30. Then I have another one in time 60, a difference of 30 time units. Then I have another one in 100, another one in 130. The difference again is going to be 30. Finally, I programmed one in 175 and the other in 230. Now let's wait for the time number 30. That is going to be okay. Now I am trapped in here, waiting for the interrupt to occur. And time 30, 28 now, 29, 30. That's it. Now I have to jump to check if the interrupt flag is activated. Yes, it is. So I have to go to the interrupt service routine. In there, I clear the flag. I check if this is the first time. Yes, it is. So I move the occurrence time to the proper rec 0 register. Then I turn on my flag and I jump out. So I'm going to wait now for time number 60. That's it. Same thing. But now I have to jump to second. That's it. I copy this time difference to register 1. And I make the difference. And I have right there 1E. 1E is 30. And obviously, I'm not going to get anything in res age since we only have 30 time units. So I'm going to jump out. Our next stimulus is going to be in 100, right there. Same thing. I'm going now to store this difference in those registers, register 0. And I'm going to wait for the next stimulus in 130. That's it. Now I'm going to start in register 1. This is the change. The difference is going to be the same, so don't expect any changes in there. And I leave, and finally, for my last pulse, right there, waiting for the second one, in 230, right there. Now, this is the second, jump to the second, obtaining the difference, and this is the difference, 37 hexadecimal, that is to say 55 time units, as expected. So our program is okay. Now we are ready to put it in the curiosity card. Okay guys, let me show you this beauty. This is the curiosity card. We have attached to it 18F45K50 microcontroller. Sorry for this spot of orange ink, but the guy at the laboratory, that is a very grumpy person, just put it in there trying to protect the microcontroller from being stolen. I don't know if that's going to serve or not. But okay, we are going to connect this to our function generator. We are not going to know what frequency do we have in there. going to connect to pins RC1 and ground. Okay guys, I just programmed a mysterious frequency in my function generator, and let's see what happens. Let's test this in the curiosity card. Let's compile this. Okay, no problems. Then the debugger. The program is properly loaded. Run. And here we have these couple of numbers, res H and res L, being 1183 hexadecimal. I'm going to use one of these marvelous apps that is called TI Inspire. That is the same calculator, but in an app for an iPad. You can get it in the App Store. And what we are going to see here is a conversion from this count into a frequency number. So this is going to be 0h1183. That makes 4483. I'm going to multiply this for the time cycle over 16 megahertz. That is 1.12 milliseconds. And my frequency is going to be 892 hertz. So let's see if this is true.